Live from your local news leader, Karina Rubio, Matthew White.
Central Illinois' most accurate forecast with meteorologist Jacob Dickey.
You're watching The Morning Show at 9 on WCIA 3.
Well, as always, we do thank you for staying with us. We've just learned that judges announced the nominees for the 2022 Nobel Prize in Physics.
That's right, and here to also give us a quick German lesson and talk about that prize is wise guy Paul Kwiat. So Paul, thanks for being here, but the big question, how are these things connected?
How are they connected? So let us start with our first German lesson. So I have just a graphic here, a word you may or may not know if you don't know German, the word Spookhefte, which translates as spooky. And that was used by Albert Einstein. So next, click on the next slide here, as in the sentence, Spookhefte Fernwirkung, spooky action at a distance. This is how he described quantum mechanics. He didn't really like quantum mechanics, although he sort of helped invent it in a way. The next word that we have is Verschränkung. That sounds a funny one. And that is a word that Erwin Schrodinger used. He's like one of the founders of quantum mechanics to describe entanglement. In fact, next slide, he really described entanglement as like the characteristic trait of quantum mechanics, the one that really makes it totally different from classical physics. Okay, and then now last we have a little Swedish lesson here. Okay, yeah, I'm not gonna try to pronounce all that. So we can immediately go to the English version here. So this past week, on Tuesday, the Nobel Prize in Physics for 2022 was announced, and it went to these three gentlemen, John Clauser and Alana Spey and Anton Zeilinger, all of whom were instrumental in trying to understand entanglement and how it's used. And so that was a really big deal for my field. So I actually know all of these people really well. And so maybe I just thought I'd talk a little bit about what does that actually mean? What is entanglement and such? So my favorite example is that if you think about, let's say, an atom that's out in outer space, it's excited and it decays and it emits a photon. And that photon goes off in all directions. Because this is what happens all the time. As atoms are excited, they decay and emit light. That's how we see everything, absolutely. So this atom, when it decays, the photon can go off in all possible directions. We don't actually need that slide just yet. So when the atom decays, the photon goes off in all directions. And because the photons actually have momentum, that means in the atom, when it shoots off this photon, the atom has to recoil in the other direction. Just like if you were to fire a gun, there's a recoil in the opposite direction. So when the atom fires the photon off, the atom has to recoil. But the photon's going in every possible direction, and the atom's recoiling in every possible anti-direction, which is a really strange kind of state of affairs. And then what happens is that when you look up and you happen to be the person to see that photon, you, and not you, unfortunately, then it disappears from everywhere else, because it's only one photon. It can only appear in one place. And suddenly the atom now is in a location. It jumps as though it had been moving away from you for the past 100 years or whenever it emitted it. So before you make that detection, the state of the photon is everywhere, going in all directions, and the atom's going in all anti-directions. That's an example of an entangled state. Okay, so you might think that really, although we don't know which way the photon's going off and which way the atom's recoiling, maybe the atom really knows and the photon really knows, that there really is some definite element of reality whether or not we know it or not. And until 1960, that was really kind of just a philosophical debate. People thought, well, okay, you're fine to say that we don't know it if that's what quantum mechanics says, but really maybe there's some underlying hidden thing that describes it. And then in the 1960s, there's this physicist, John Bell, who said, no, I devised an experiment that would give different results for that kind of a model where the particles actually know where they're going, and basic quantum mechanics, which is say you can't actually know where they're going. And then, okay, so now we can, and he came up with this thing called the Bell inequality. It's just a theoretical way of distinguishing between those two. So then along comes John Clauser in the late 1960s, and he comes up with an experimental way to test that, so that you could actually do in an actual experiment. He does the first experiment, and in fact, it shows that no, this model where the photons know where they are is wrong. But there's quite a few loopholes in his experiment. And so 10 years later, Alain Aspect in France does the experiment quite a bit better and closes some of these loopholes. And in fact, he wrote the article he wrote on that inspired an article that I read when I was an undergraduate in physics, and that's why I became a quantum physicist, actually, was on the basis of that article. Okay, and I actually knew John Clauser. We were both at Berkeley together when I was a graduate student. He was kind of a scientist there. Okay, and then finally, Anton Zeilinger, another year, 10 years later on, adopted a much better source in which to make entanglement that I actually helped develop. I was his postdoc in Austria at the time, and was able to use that and do applications like quantum teleportation and other things like that. And so this is really a kind of a big week for physics, and in particular for the whole area, my whole area of quantum information, because everything is really built on entanglement. The entanglement is sort of like the dilithium crystals, if I use a Star Trek analog. It's like the warp engine for all of quantum information science. So it's been a big week for us.
Kind of full circle for you, too, to be talking about it on the morning show here after working with them, years ago.
Indeed. So maybe I'll talk a little bit later about some other applications of that.
Well, congratulations to those three as well, for sure.
All right, Dave, thanks so much for being here.
Thank you.
And we'll have your